Hi guys, today we will do section 5.6, definite integral substitutions and area between the curves. Let's get started. Learning objectives are, so we'll do the substitution formula. We already learned substitution, right? Use substitution. Now, how do we apply it for definite integrals? And then how the symmetric functions can help us in handling definite integrals. How can we implement these ideas in finding the areas between the curves, and we also discuss the cases where we need to do integrate with respect to y instead of x. So let's get started. So if you remember the use substitution, what we had was, if you have an indefinite integral f of g of x times g prime of x dx, then I could integrate it using a much simpler form, f of u du, where I set it u is equal to g of x, right? This is what we learned. So now this theorem 7 is telling us how you would apply these ideas to definite integrals. So why it's definite integral? Because we have limits, right? Now we expect a number here. So the only change is you have to basically consider appropriate limits. On the right hand side you have an integral of u, so you cannot simply use the a and b here, right? You have to do something. Okay, what are these a b? Well, a b's are the bounds for my x, right? Here x is a, x is b, and because of this g of x is equal to u, when x is equal to a, your u becomes g of a, right? And similarly, when x equal to b, the upper limit of the integral, your u becomes g of b, right? As we can see. So that's the transformation you need to do in handling definite integrals after you applied u substitution, right? You have to be careful with this limits. It's one of the confusing parts sometimes. All right, so let's consider the following example. So integral from -1 to 1, 3x squared, square root of x cubed plus 1 dx. How do we find it? There are two methods. The one method is shown in the previous slide, so let me first handle with that method. So first way, following. Well, u substitution is not hard to guess. We can do u equal to x cubed plus 1, which gives us du equal to 3x squared dx, and we already have 3x squared dx, so that goes into du. So let's compute the indefinite integral first, right? So this 3x squared x cubed plus 1 in square root dx simply becomes, after this substitution, it becomes square root of u du, right? Okay, what is this? What is the antiderivative? Well, square root of u is u to the 1/2, so this is u to the 1/2 plus 1 makes it 3/2 divided by 3/2 plus a constant, right? So that's the indefinite integral. Now let's go back to our definite integral and let's find the limits. Well, when x is -1, my u is going to be, so you substitute x equal to -1 here, you will get 0. When x is 1, then u becomes 1 cubed plus 1, this is 2. So my integral, after I make all the substitution, becomes the following, right? So I will get integral from 0 to 2, and my, let me write the square root of u du. But since I already know the antiderivative of square root of u, that I already did it here, the c's cancel, so we don't have to write c. It becomes, okay, let's say 2 over 3 u 3 over 2 evaluated from 0 to. So at 2 you get 2 over 3 times 2 to the 3 over 2 minus, we use 0, it's 0. So this is 2 over 3. Here 2 cubed is 8, so this is square root of 8, etc. So if you want to simplify further, this is 4 over 3 square root of 2. So this is the sort of use substitution for definite integrals. Now I will show you another method which is also doable. The first part is more or less same, but the second part is slightly different. So the second way, we basically do the same substitution. There is no change whatsoever with this substitution. This gives me du is equal to 3x squared dx, etc. So at the end, I'll get something like square root of u du, which gives me u 3 over 2 divided by 3 over 2 plus a constant. But now here is the different why it's the second way. What is the specialty? Well, instead of u replace u by x cubed plus 1. So this becomes 2 over 3 times x cubed plus 1 to the power 3 over 2. Okay? Alright, so now how do we, so this is just the indefinite integral part, right? But how do you handle the definite integral? Well, what you do is, we already know the antiderivative, it's given right here, so you simply write 2 over 3 x cubed plus 1, 3 over 2, and you simply evaluate from -1 to 1. Why it's -1 to 1? Because you remember these limits are for x, right? These limits for x, and I have a function of x, so you don't have to change. If you leave your integral as u, then you need to use the corresponding limits like we did in the previous slide, right? 0 and the 2. But here, because I went back to my original variable x, I use my original limits, -1 to 1. So then you substitute x equal to 1, you get 2 over 3. Here you'll get 1 plus 1, 3 over 2, and you replace x equal to -1, you get 0, right? So here it's 0. So as before, I think at the end you'll get 2 over 3 times square root of 2. All right, so let's do a couple more examples. Well, let's say u is equal to cotangent theta. Why cotangent theta? Well, when you take the derivative, you see cotangent theta is minus cosecant square theta d theta, right? So we already have those things except for minus sign. So we do it minus the integral u du. Now we need to decide for the limits of integration, right? So when theta is pi over 4, what is u? U is cotangent pi over 4. This is 1. When theta is pi half, cotangent pi half, this is cosine over sine. Cosine pi half is 0, so this is 0, right? So what I have is, this is the integral is from 1 to 0. It's not from 0 to 1, it's 1 to 0. All right, so now integral for u is u squared over 2, evaluated from 1 to 0. At 0, this is going to be minus 0. At 1, so we have minus is going to plus. At 1 is 1 over 2, hence this is 1 half. Okay, how about the second one? Well, we already discussed integral of tangent, so if you remember, then you can use its antiderivative. However, we can quickly derive it one more time. So let's do it. So first you write it as sine x over cosine x dx, and then you let u is equal to cosine x, which makes du equal to minus sine x dx, right? So this is going to be minus sine x dx is du divided by u, right? Okay, we can follow the similar method as before. Let's see what happens for theta. If theta is minus pi over 4, then u, which is cosine minus pi over 4, is the same as cosine pi over 4. So this is square root of 2 by 2. And when theta is pi over 4, u is going to be again square root of 2 over 2. So my limits for the integration in terms of u are square root of 2 over 2 and square root of 2 over 2. Well, when you integrate from one point to the same point, I mean, it means you don't have an interval, right? So it becomes, regardless of what you have here, okay, you have like minus, I mean, you can write it like it's minus ln square of u, and you evaluate from square root of 2 by square root of 2 over 2. Well, you will see that it's simply 0. Okay, definite integrals of symmetric functions. If you look at the picture shown in A, we see an even function, right? We have an even function, so it's symmetric with respect to y-axis. Well then, if the function is symmetric, why do we need to integrate from minus a to a, right? All we can do is we just integrate from 0 to a and just multiply by 2, because sort of in a sense, area here is same as area here. So we don't have to calculate the area twice, and that might simplify sometimes. Even better, if your function is odd, so like in B, right? The function is odd, so odd means it's symmetric with respect to origin, right? With respect to origin, it's symmetric. So here's the peak, here's a point, here's a point, etc. Right? So the graphic symmetric. Then, if you integrate from minus a to a, well, the things cancel out, right? So this is positive area, this is negative area, they cancel. This is positive area, this is negative area, so they cancel out. So here the integral becomes 0, right? So it's summarizing, that's what we have. If the function is even, instead of integrating from minus a to a, you can integrate from 0 to a and then simply multiply by 2. If the function is odd, then if you integrate from minus a to a, it's just 0. Okay? Okay, let's consider the following integral. Well, the function that we have, f of x, which is x4 minus 4x squared plus 6, this is even. Why it's even? Well, if we start with f of minus x, right, minus x to the power 4 minus 4 times minus x squared plus 6, well, because of this even degrees, we get back x4 minus 4x squared plus 6, so we get back our original function f of x, right? So, which means f of minus x is equal to f of x. Thus, to evaluate this, all we have to do is just evaluate it from 0 to 2 and then multiply by 2, okay? Not sure how much it simplifies, but anyway, so let's do it. So 2, antiderivative here is x5 over 5 minus 4x cubed over 3 plus 6 times x from 0 to 2. Yeah, here's a nice part, right? When I evaluate at 0, everything, this is 0, right? So all I have to do is just evaluate at 2. So that's why this is kind of much simpler. So you evaluate at 2, it becomes 2 to the power 5 divided by 5 minus 4 times 2 cubed divided by 3 plus 6 times 2. And here we get minus here. You need to multiply everything by 2, but 2 times 0. Right? So once you evaluate the first part, you're essentially done. So areas between two curves, right? So you have a function y is equal to f of x, and we have a y equal to g of x, and let's say that we are interested to find the area from a to b of the region enclosed by two curves, right? This blue region. How do we do it? Well, in the previous lectures, we discussed simply the area under the curve, right? So what that means is the area between the curve and the x-axis, right? Now there is no x-axis, we want to restrict ourselves with another curve, right? So this is a slight change, but the idea is not much different. So again, you sort of slice your interval AB, right? To consider the partitions, right? And then again, you pick some xi here somewhere, and then you, according to this xi, you look at this rectangle here, right? And then simply compute the area of this rectangle. Let's call it delta A, right? So what is the, let's call delta AI, so ith area. So this is going to be what? So this point here is your f of xi, and that point, sorry, that point is here. So that point here is your g of xi. So we already know the width, right? So width is delta xi, right? So here width is going to be delta xi. But what is the height? Well, height is your the difference in y coordinates. So this is going to be the f of xi minus g of xi, right? So this is your height. You multiply by delta xi. That gives you the area of this small rectangle. And then to find the whole area, right, the area, what is it? It's going to be the sum of all these areas, right? Sum of all these areas, or if you like, but then I need to make it consider smaller partitions, right? This delta x needs to get smaller, so basically I need to take a limit as n goes to infinite of I, let's say from 1 to n. So let's say my partition has n elements, so this is the same as limit n goes to infinite. Now let's write it in the Riemann sum form. So this is fxi, so upper function minus the lower function times delta xi, right? And in the end, what is it? Well, you get simply a definite integral from a to b fx minus gx dx, right? So that's the area formula. So summarizing, if you have two continuous functions where f of x is greater than or equal to g of x on an interval a b, then the area between this curve can be found as an integral from a to b of f of x minus g of x. So you remember the area must be positive, so I need to make sure that this is non-negative, right? It needs to be non-negative. That's why this requirement. What happens if sometimes it's flipped, right? Sometimes f is bigger than g and sometimes g is bigger than f. It means then you need to split your interval accordingly. So let's do some examples. All right, so we'd like to find an area bounded above by 2e to the minus x plus x and below by e to the x over 2. So somehow we are already given the hint that this is this function is bigger than that function, so you don't have to try to find which one is big, etc. And on the left x0, on the right x1. So here's the picture. So whenever possible, you need to try to sketch the picture because it will give you idea how you should proceed, right? So here I'm integrating from 0 to 1, and my upper function is 2 times e to the minus x plus x, and my lower curve is 1/2 times ex, right? So then, well, by the formula, area is nothing but integral from 0 to 1. This function right here, so 2e to the minus x plus x minus ex over 2 dx, right? Okay, well, integral of e to the minus x is e to the minus x multiplied by minus, right? So this is minus 2e to the minus x. Integral of x is x squared over 2. Integral of ex is ex itself, so here we have no change. Evaluated from 0 to 1. So at 1 I get minus 2 e to the minus 1, so it's minus 2 over e. At 1 I get 1 over 2. At e to the x I get minus e over 2. And then what happened at 0? Well, at 0 I get some here minus sign, so minus is going to be plus. 2 times e to the 0 is 1, so just 2 times 1, let's say. And then we get plus, so but I need to subtract, so it becomes minus. At 0 this is simply 0 over 2, and then minus is going to be plus. At 0 this is 1 over 2. Okay, so whatever you get from here is will give you the area. All right. Now we're given a parabola y equal to 2 minus x squared. So this is a parabola opening down, and a line y equal to minus x. And I would like to find the area of the region enclosed by these two curves, two graphs. Well, the picture is shown on the right, but here is a slight change from the previous one. We are not given the limits of integration, right? From where to where, right? On which interval I need to find the region? Well, it says enclosed, which means I need to find the intersection. So these two curves are going to intersect. I mean, we can see it from the picture here, one point, and here another point, right? So we need to find these points, and then we can get started with the integration. How do we find the coordinates where two functions intersect? Well, we have to equate the curves, right? So we say y is equal to 2 minus x squared, but y is also equal to minus x, right? From here, we get x squared minus x minus 2 is equal to 0, right? Well, minus 2 is can be factored as minus 2 and 1, so you multiply the 2, you get minus 2, you add them, you get the coefficient of the x. So this is x minus 2, x plus 1 equal to 0, which gives me x minus 1, and x is 2. So these are the limits, right? So here's 1 minus 1, and here is my 2. So I will be integrating from minus 1 and 2. So area is the upper one is the parabola, so it's 2 minus x squared, minus the lower one is minus x, right? So minus x dx, which is 2 minus x squared plus x dx. Yes, one way to check whether your answers are correct is for the area you should be getting something positive, right? If you somehow end up with a negative value, it means there is something wrong. Maybe you messed up with this f minus g. Maybe somehow you wrongly make it g minus x, etc. Right? So you have to be checking with your answer. Anyway, so integer derivative here is 2x minus x cubed divided by 3 plus x squared over 2 evaluated from minus 1 to 2. Well, at 2 this is 4 minus 8 over 3 plus 4 over 2. At minus this is going to be minus 2x, so this is you subtract. So let's make it let's be a little careful. So minus, so here it's minus 2, at minus 1 this is plus 1 over 3, at minus 1 this the last one is 1 over 2, right? So if you simplify, I guess you get 9 over 2, which is positive, so it looks like we did it correct. Let's hope that we did it correct. Now integration with respect to y. Why do we have to do it, right? Well, it might happen that your curves are better defined in terms of function of y, right? Like it's not like y is equal to f of x, it's x is equal to f of y, etc. So, for example, if you want to do it using the technique that we use, so you want to integrate with respect to x, you should be splitting, right, slicing your intervals vertically, right? When you split, it gets messy, right? So you see that it gets messy. We don't have an appropriate formula for the height of the rectangles. However, if you slice your interval, let's say from C to D, horizontally, then we denote this width to be dy, right? Because it's the change in dy, and our height is essentially what? It's the difference between f of y and g of y, right? So this height is now going to be the difference in x-axis. So difference in x-axis is f minus g. Okay, so this means at the end of day the area can be computed as integral from C to D f of y g of y dy, right? So everything in terms of y. All right, so let's say that I want to find the area of the region in the first quadrant that's bounded above by y is equal to square root of x, below by y is equal to x minus 2. So everything given like in terms of x, so it looks like I need to be integrated with respect to x. But wait a second, so, and also by x-axis, so if you try to sketch the graph, this is what you get, right? So this the area that I'm looking for is this sort of orange area plus the blue area, right? So I should be integrating from 0 to 4, right? So from 0 to 4, and then if you want to do it with respect to x, right? If you want to do with respect to x, what should we doing? Well, in the first part, right, from 0 to 2, I only have one function. So I need to look at only one function and then integrate, right? And then here it's just y equal to 0 also. But from 2 to 4, I need to consider both functions, right? I need to consider this blue curve and this yellow curve, right? So there it will be different. See? So here in the first occasion, I have this integral. In the second part, I have that integral, right? So this is kind of doable. It's doable, but somewhat time-consuming, not very convenient. So instead, we can think, okay, maybe we should consider integration with respect to y. Well, if you try to integrate with respect to y, things get easier, right? Because then the region is simply bounded sort of above or from right by this yellow curve, and from below, so from left, by this blue curve, right? So at the end of the day, I will only have one integral. So let's try this one. Right. So our small area A is roughly the difference between the yellow and the blue. But what is the yellow one? Well, it's y is equal to x minus 2, but I need to solve for x, right? Because I need to compare their x-axes. So you solve for x, it becomes y minus 2, right? So, sorry, y plus 2. So here, y plus 2. So this is going to be y plus 2. And then from below, I have this y is equal to square root of x, which means x is equal to y squared, right? Because again, I need to find x coordinate. So x coordinate is y squared here. Here the x coordinate was y plus 2. So then you take the difference, right? So minus y squared. So that's the height. And then my width is dy because I'm slicing horizontally, right? Whenever you slice horizontally, it's integral with respect to dy. Whenever you slice vertically, it's going to be dx. Right. So basically then applying the Riemann sum and taking the limits and so on and so forth, eventually area becomes the integral of y plus 2 minus y squared dy. And where are my limits, right? Where are my limits? How am I slicing? So I'm slicing horizontally, right? So I start from 0 until I reach this point, right? So again, because my integral is with respect to y, I need to look at the limits on y-axis, not on x. So you shouldn't say like from 0 to 4. No, it's from 0 to 2. So 0 and 2. Right. So once we set up the integral, the rest is easy. So y squared over 2 plus 2y minus y cubed over 3, evaluated from 0 to 2. So this is 4 over 2 is 2. 2 times 2 is 4. Minus, here we get 8 over 3. And then when you let y equal to 0, everything becomes simply 0. So this is 6 minus 8 over 3. 3 times 6 is 18, so 10 over 3. So that's the area.